This image shows both physical and logical representation of a pointer variable. On the left side here, right, we have physical representations. This is where data and pointer variables exist in memory. The logical representations here shows the relationship rather between both variable, right, and the pointer without the physical details. So P, right, the pointer variable, points to the variable that exists in different locations here. Now, if we look at the physical representation, we see that this P or pointer having this value, and this value happens to be the value, right, or the address of these variables that sits in the different memory locations. The memory address of A is referred to as the unary expression, so we need to apply that on top of the variable, and that gives us the memory location of A, which is stored as the value inside this P. Now, this P also has its own memory address, which is not shown here. So just wanted to mention that there is a distinction, right, between a variable and its value. A variable has a memory locations. Now, a value is simply just a literal, right, that is stored inside that variable according to the type that this variable represents. So in both instances, since A, right, is an integer, P wouldn't be declared, right, as a pointer, integer pointer that points to the memory address of A, okay? And this asterisk, right, is the pointer, right? So you have to have this asterisk, right, at the end of your variable, right, to specify that this P itself is actually a pointer. Now, whether a pointer is a data type or not is subject to debate because a pointer is also taking up some memory space. So in fact, if you do size of, right, pointer, this will actually give you 8 on most contemporary machines. So which means that this pointer itself occupies memory address. Now, although in C and C++, pointer is not officially defined, right, as a data type, but some people call it as a data type since it does occupy memory spaces at runtime. This slide shows that we can actually place the memory address of a variable that we declare either on the stack or a heap. Doesn't matter, in multiple variables here. So there's integer pointer P, there's another integer pointer Q. In fact, at runtime, there's no limit as to how many pointer variables we can have or declare, and then have them defined to have value of someone else's memory address. So you can have like 4 or 5 different pointer variables all pointing to the same, basically. What would be a good default value for a pointer? Let's say we have an integer pointer P. Let's say at runtime, there is not another variable where we can point this P to. It then is best as a good software engineering practice is to always initialize your variable. So in this case, we assign this null value, right, to P. This null is actually a macro in C++ that has a value of 0 at runtime. This is good because you can tell your program that there is nothing else that this P is pointing to at any given time, since there is no such thing as a 0 memory address, right? So memory address of a value of 0 simply does not exist. So this is a good default value to use for pointer when there is nothing else that this P is pointing to. Now, effective C++ 11, they introduced what's called NULLPTR. Now, this is the same thing as NULL, right, capital, but NULPTR is the lowercase. This one is actually what we call type safe pointer because this differentiates what a 0 versus what a pointer type is. As you know, NULPTR and ULL have, both of them have value of 0. So at runtime, when you pass this pointer into a function, let's say that expects an integer, you can pass it as a null. But however, if this is NULPTR, you can't just pass this a pointer to a function that expects an integer because NULPTR is a pointer type. Okay, it's not an integer. So we'll get into more about this is when we get into C++. But suffices to say you can use either NULL, right, uppercase, or NULLPTR, lowercase, effective C++ 11. And this one actually works in C as well. Now we're going to introduce this concept called dereferencing. But before we get into that, let's introduce this other unary expression. And this one is actually an asterisk. Now this asterisk is not the pointer type, right? When we say integer asterisk, right? This asterisk is not the same as that one. In fact, we use asterisk in front of the pointer variable type. Let's say if this is asterisk and this is a pointer, right, variable. So usually we use a, right, as a pointer variable. So the convention is this, right? So if you have, let's say, an integer pointer, right, p, that points to the memory address of a. What is a? A is an integer, right? Let's say 5. So at runtime, right, this memory address for a sits right here, and a has a value of 5, right, associated with it. But how do you get 5 through pointer, right? So this is the trick here. We use this indirect expression. Another word for it is dereferencing. And using this extras allows us, to dereference a pointer to get this value 5. Now, in the next slide, we're going to talk about how we do that from a mechanical standpoint. Let's take a look at this slide and what's going on. The premise is here that we have this integer. X is actually integer because we see that integer is being used throughout as the value of x here. So what about P and Q? P and Q are actually integer pointer. So the way that we have set up here, since P and Q are both pointing to x, so it has to be the memory address of A, right? Remember, this is the unary expression, and this is the pointer type, right? This entire thing. So it's not the dereferencing operator here. So similarly, we have integer Q, right, equals n% of A right here. This is what happens with respect to P and Q's initializations here. Now, initially, we don't know the value of x. So maybe at some point there's an integer x somewhere, right? Now let's put everything in perspective with respect to P and Q, right? Starting from this point on, and then let's just move down. So initially what we have is this integer x, right? This integer x right here is a question mark. So there is nothing assigned to it. That's it. And then we have P and Q. What are P and Q? So P and Q are integer, right, pointers pointing to the address, right, of x right here. So is Q, right, address of x. So that basically says it, right? P and Q are both pointing to x, however, x has no value to it. But as soon as we say x equals 4, that's what we have here, x equals 4, then what happens is we put a value of 4 into it. Now, P and Q are still pointing to x, right? There's no changes in there. Now, if we do x equals x plus 3, now x was 4 before, and now the new value of x is 7 because 4 plus 3, 7. Now changes the value of x, and P and Q are still pointing to it. There's nothing else there. If you put the asterisk, right, this asterisk in front of a pointer variable, this is what we call dereferencing. Okay, so dereferencing actually get us to the value of P or the value of x actually. That P is pointing to. So P and Q are still both pointing to x. However, if you dereference P, you actually get the value of the value section of this x. Now, this value section of the x, right, is assigned a value of 8 at that point. So this, by virtue of doing this, you're changing the value of x. Okay, so this P, right, start P equals 8 is equivalent to just writing x equals 8. Now, this is a little tricky though, right? So this is definitely a new concept that we want you to memorialize here. So what you're doing here is by dereferencing by using the indirect expression, right? You are, instead of pointing to the x, right, memory address, you're pointing to the x's value section. Now you're effectuating change on the value of x, not the memory address. The memory address doesn't change, right? Memory address of x is still the same as before. Now, let's look at the next step, right? This next step is a little bit complex here. We have this, right, asterisk, right, and this ampersand now in front of a variable. Now you have to understand one of them is the address of x and the other one is the value of x, right? Both of these variable actually cancels each other, the effect of it. You can think of ampersand as like getting the right? The address of this variable, and the other one is getting the value of it. So when you put both together, this inverse relationship actually cancels each other out. So what you really have here is x equals, right? What is a dereference q? Dereference q actually is the value, right, of this x, which is 8, right? From this point on is 8. Now, what about the dereferencing p here? This gives you the value of x, which is 8, right? So 8 plus 8 equals 16. So this means that by doing this, right, this complicated statements here, what we're getting is we're setting, right, the value of x to be to have a value of 16. That's what this is, this entire line. Now, the very last line, right, and notice that x is 16, right? Now, if you dereference p and q, and remember p and q are still pointing to x, right? They're still pointing to it. Now, this is 16, and this is 16. So what's 16 times 16? This is actually multiplications. 16 times 16 actually gives you 256. So this is saying that you're setting x, right, to have a value of 256 using these pointers. So as you can see here, the use of pointer is very, very important and versatile. In general, a pointer allows you to access the memory address of the variable that it is pointing to. Not only that, a pointer can also be dereferenced or indirectly using the indirect expressions to fetch the value of the variable that this pointer is pointing to. So you can quote unquote remote control a variable from afar. So if you think of it that way, pointer is what makes it really, really versatile. In general, you don't have to, let's say if an object is really big in memory, at runtime, you can use pointer arithmetics to manipulate these variables, including fetching their values. Instead of passing these huge objects from one function to another, you'd be passing the pointers. And then you can still have access, right, to that variable's value at runtime. So let's look at this, right? So this is the same as saying, start ampersand x. And in fact, if you look at this, right, what gets evaluated is this first section first. So what is the address of x? Address of x is the pointer, right? And if you put extras in front of the pointer, you're getting back really itself. Right? This is the reason why this and this, right? These two, when put together in this fashion, they just cancel each other out, the effect. And this is the same, right, as saying that x equals, right, whatever this is.